Yeah, hi, Professor. Hello, everyone. Is I audible?
Yes.
Yeah.
Yes,
Welcome
yes,
you
sir.
back, all of you, for the session on the microgrid technology. Without delaying, I'm handing over to Professor Saad Mekhilef. Uh, Professor, you can go ahead of sharing the screen.
Okay, so thank you very much. So let me window. Can you see my slide?
Yeah, it's loading.
Yeah, yes, sir.
Yeah, fine, Professor.
So is it on the slide mode?
No, it is not in the slide mode.
Okay, just a minute. How about now? Huh?
Yeah, it is not yet.
Yeah, it's mine. It's okay.
Maybe you can select directly instead of sharing the complete screen.
Mm-hmm.
You just go to the present. I mean, you stop sharing the screen, sir. I just guide you.
Okay, stop sharing. All right.
Yeah, stop sharing the screen.
Stop presenting.
Stop presenting, and now you just go for the presentation and go for the presenter mode. Go for
Sorry?
the presentation. You just go for the presentation mode first, sir.
Oh, go for presentation mode. Okay, because here it shows. Okay.
Then after that.
Oh, yeah, but like this, it shows on my two-screen display. Let me in display. Duplicates. Yeah. Okay. Yes, these two screens.
Yeah, then you can share the presentation.
Display. How about now?
Yeah, I can go for share the screen, sir. No.
Yeah, done.
Go to
Is it okay now?
No, it is not in the presentation mode. No, no, actually, if, before going to the this particular share the screen, you need to go for the presenting mode, sir. Hello.
Okay, yeah, I'm trying. Let me try. Let me disconnect this. This one. Let's see. Okay. So now, okay, go on the presentation. Put on slide mode show. Okay, now it's on the slideshow.
Yeah.
But when it is in the slideshow, I cannot see the Google Meet where I can share because I'm not familiar with Google Meet. I usually use Microsoft Teams. You know?
Okay.
I'm not sure. Yeah.
No, again, you go for a share screen, sir. Please go to the share screen, and then you can select your presentation there.
Okay, so now
Share.
I am in stop sharing.
No, go for a share again.
Okay, share, present. Okay.
Go to the window. Window is there, right?
Okay, when there is a Chrome
tab and window, is
window and
Yeah.
entire screen.
there. Yeah, window is there. Go to the window.
Okay.
And then you can select the PowerPoint slideshow is there, right?
Yes.
Yeah.
Yes. I selected.
Yeah.
Then it's sharing now.
Yeah, it shares.
Okay.
Sir, if it is better, you can share the entire screen.
Yeah. Let's try. Let's try
The
start
entire
sharing. Share the entire screen. Entire screen. Okay. Okay. This one. All right. And then, how about this now?
Yeah, now it is fine.
Now it is fine.
Okay, good. Okay, so I think it's good morning there, and so thank you very much again. So we would like to start our first lecture on microgrid technology. I think what we are going to look into this during this lecture today. I think we have two lectures. See, the first lecture we'll be looking into the issues with the traditional power network. So we have an existing power network which has been exist for almost 100 years, and there are many issues on this traditional power grid, and the new technologies, how they have been integrated into this power grid. Because this power grid took almost 70 years to build, and it's still working, and it's still going to remain, actually. And then we will define what is microgrid, okay, and why do we need a microgrid, okay? So this is also the need. Why do we need this microgrid? So very important to know why do we this microgrid need, and then we look into the benefits of the microgrid. Okay, what are the benefits of the microgrid? Okay, and the main components, because this microgrid varies from different types of microgrids. They are vary, so they have a different configurations and different components. And then look into the renewable energy sources, because one of the main component of all microgrids is the integration of renewables into this in it. So it always comes with the renewable energy sources. And we look into mainly the solar, and then the wind, and then in the solar also we will be looking into how we design the solar systems, what are the components of the solar systems, how to select the inverter, how to select the PV modules, how to select the things, how the PV modules works, Then we look into the MPPT control techniques and things, and then we look into the wind also, and then microgrid operating modes. So these microgrids actually they can operate in two modes mainly, either is grid connected mode or it is a standalone mode. And then microgrid configurations. Okay, so we have a different. We have actually mainly three types of microgrid configurations. One is AC. It's a purely AC microgrid, or DC microgrid, and sometimes we may have a hybrid, or we call it harmonized DC and AC microgrids. And then some examples of microgrids. So this is what we are looking today. So today in modules we will be looking into this. Maybe the first one half an hour, and then the second half. Okay, so if we look into the traditional, is the slide moving? I'm in the second slide.
Yeah, slide moving, sir.
Yeah, good. So please let me know in case the slide is stuck somewhere. Please let me know so I can refresh it. Okay. Yeah. So traditional power networks, it consists mainly from three components: it's the generation, transmission, and then the distribution. So in the generations, we will have all the traditional power plants, like the coal power plant or gas power plant, or the traditional compound. And then most of the time we will have the step up transformers to increase the voltage. Okay, and then we have the transmissions, and then when it goes to the distribution, then we have step-down transformers, and then it goes to the factories or to the homes or whatever, you know. So this is the traditional grid. It's, you can see it's a one-way, means from the generation to the distribution. It is very rigid, means you can see you cannot change much. You cannot remove one component of this. If you remove one component, the grid systems will collapse. So it's very rigid. You know, you can see generation, transmission, distribution, and then you have transformers in the between, and that's it. You know, very rigid, very it's called it one-way communications or one-way power transfer. So this is the traditional grid. So what are the issues of the current traditional networks or grid? And this grid, as I said, it has been built for almost 100 years now. So it's not something that we can easily dismantle or easily remove. It has been built and built and built and built, you know, year after year, and expand. And not now, it's not only one grid, one country. It's now, it's interconnected. Different countries also, they have interconnected grids. Okay, for example, you will, for example, in Southeast Asia, you can see, for example, from Laos to Thailand to Malaysia to Singapore to Indonesia. All these are grid connected. It's one grid. So it's becoming expanded. It's becoming very large and very huge. And I think the same in India. Maybe India is connected to Sri Lanka, you know. And so these are the grid. Traditional grid is expanding and it's getting larger and larger and larger. So one of the main characteristics of the traditional grid is a dependence on the fossil fuel. The main source of electricity on this traditional grid is generated from either burning the gas or the coal or the oil. Okay, so these are the main three sources. Sometimes maybe some countries, they have some nuclear, okay, nuclear, which considered also as a part of the traditional. So, and some maybe they have some hydro power, you know, the traditional hydropower, large hydropower. Yeah? But mainly the three component, which is either is a natural gas, coal, and oil or petrol. Okay, so it's been, as I say, it serves the world for almost 50, 60 years now. But one of the things is they have a very high in gas emissions, you know, a lot of gases, a lot of emissions. And we seen in the last few years the effects or the impact of these emissions on the planet. You know, we have seen a lot of floods. We have seen a lot of what you call disasters happening, and that's due all to these emissions. You know, so it's a lot of emissions which actually causes this kind of disasters and floods. You know, we experience heat. We experience extreme temperatures. You know. So this actually due to those emissions. And these traditional power plants usually are not close to the demand centers. Okay, so most of these power plants, they are built far away from the load side. Okay, far away. For example, when you have a coal power plant, you cannot put the coal power plant inside the city. It has to be far away because there is a lot of emissions, there is a lot of dust and so on. The same thing goes for nuclear power plant, for example. It has to be very far away. So when they are very far away from the load, so you need to have the transmission lines, expensive transmission lines, okay? And not only these transmission lines is expensive, but also they will introduce losses. So we will have a lot of losses in this transmission line. So we call so a lot of losses. Okay, so that's why most of the time we will have like a 20% extra power generation in transmission line which never been used, because just to cater for these types of losses. So what we need to balance between generation and demand always. So that's the issue. So when you have a high demand, then you turn on your gas generators, you turn on your nuclear power plants, or you turn on your coal power plants. But as I said, this grid has served, a lot. And then, so one of the issues, it's a lack of flexibility. Okay, so it's very rigid, means, very rigid means it does not accept high penetrations of renewables. For example, if you have so many houses having what I call photovoltaic systems, so they don't accept this high penetration. Maybe small penetration is fine, but at to reach a certain limit, then becoming disturbing the grid. So it's very rigid, and also it has a very complex control. It has very complex control, and what I call let me take the pen. Yeah, it has a complex control system, because it's huge. So the complexity is very, very the complexity of the control is huge. Also, it's not flexible, like I say. It does not accept any additional generations, and it is a passive network. It's a passive network. What does it mean, passive network? Means as a user, you cannot generate energy. So or you can generate a limited amount of energy to the grid. You cannot inject a lot of energy. So that's why most of the participants or the users are passive participants. So existing grid present an issue with the DC loads. So this is another issue. If you have DC loads, because all this grid is AC, so in nature. So when we do DC loads, for example, DC motors or DC computers or DC, all the ITs are DC in nature anyway. So what will happen? That we have to rectify, and then when you rectify, this harmonic will be injected back to the grid. So that's actually the main one of the issues. So it's not very friendly with the DC loads. So these are some of the issues that actually exist in the traditional power networks. So, but what is the new current? How the current networks or the current grid is transforming? What you can see from here, okay? First one, you can see there are these green blocks. These green blocks, what does it mean? Means actually there is a two-way power flow. Okay, means you can be as a user, and you can be as a generator, or you can be as a load, or you can act as a generator. Okay, this is number one. Means it's becoming the grid now moving into. That's why I put between brackets. It's a current. It means it's transforming. It's still not yet, but this is the future. The future will be this. So what we will have a lot of renewables. We will have a nuclear. We will have even the gas and the hydro power plants, solar, electric trains, electric vehicles, homes. So we will have a lot of what I call users or participants, which actually can accept and also can inject the grid. Okay, and also what you can see also in this diagram, you can see also that this yellow line. So previously we only transfer power and one direction. So now we transfer bi-directional power. Because, for example, like when you want to buy your, for example, electric vehicle, now we see V2X. When we want to purchase the electric vehicle, we have few options. We see V2, V2G, V2H, V2L, V. But now there are some options where you can opt for V2X. What does it mean, V2X? V2 V means electric vehicle to electric vehicle, V2H, V2 home, V2 grid, V2 MG to microgrid, V2L, V2 grid. So you can actually not only one, but it's too many sources, and that's what will be the trend in the future. It means the future will be moving into more into power and data. So when we transfer, that's why this you can see this orange or yellow line. Actually, this means they are communicated, and sometimes they are communicated wired, and sometimes is wireless. Okay, so they can be also wirelessly communicating. So because we have a lot of information, because we need to share the informations, and how much being connected to this, for example, to these networks, and then how much can be connected. And maybe we can also ask someone to come in, and connect to the grid. So this is the new grid, and it is starting now. We see a lot of, for example, here in Australia, we have almost 3 million houses, out of 6 million, almost 50% of the houses have a grid, have photovoltaics on the rooftop. Okay, that's very huge. And then we see a lot of countries, for example, which have a lot of wind, and I think India have a lot of wind power, especially in the southern parts of India. We have seen a lot of solar power plants. China is also leading in this. So we see that actually the grid is transforming. Okay, so you can see the traditional grid and the current grid. So now let's look into the microgrid. We call it micro because it's smaller. It's not a grid. Grid, it's huge. Okay, talking about gigawatt level, but microgrid is a smaller in size. So what is a microgrid? Okay, microgrid is considered as a locally confined and independently controlled electric power system. So it's a small network which is locally controlled. Okay, it means you can control it, you can turn it on, turn it off, you can add sources to it. Okay, so it is locally controlled, and it has automatically should have the load. It should have the distributed sources, such as solar or a diesel generator or fuel cell or whatever, So you can have different combinations. It depends on the available resources you have. For example, if you are in a remote area where you're having a river next to you, so the best is to have a micro hydro turbine, because you have a river, you have water, running water, so you can make use of the micro hydro, plus maybe solar. Maybe if you are in the deserts, for example, where there's a lot of sun, you can have solar, maybe storage, maybe a diesel generator, or maybe the grid itself. Okay, so this depends, because we have two types. We have either grid connected or what I call isolated or independent. So you have these two options. Okay, so if you look into this figure, okay, if you look into this figure, what you can see this is a typical microgrid, but you can see here this is a grid connected. Okay, so what we have, for example, here we have a wind turbine, we have solar PV modules, we have what I call micro turbine, which is basically a diesel generators. We have a fuel cell, we have storage. Okay, so what does this mean? It does not mean that you must have all these components. No, you can have. This is just an options. The options that we have. Okay, and then we have here, for example, we have the load. Okay, so you can have only wind, and because if you ask me, you will not have this kind of microgrid, because you do need, you have fuel cell, you have diesel generators, you have storage, so these are too many, too expensive to build. But these are the options. Okay, you may have wind and solar and diesel generators only. You may have solar, wind, and storage. So the combinations depend on the availability of resource, because the idea of this microgrid is to make use of the local available resources. So that's the idea. The idea is to make use of local available resources. Like I said just now, if you are in a remote area where you're having a river, a stream next to you, so number one is to use the micro hydro turbine. So because you have available resources, and then you look into, does this area have a good solar access? Yes. So if the area have a good solar access, then we should have solar photovoltaics. If the area has, for example, good, maybe access to hydrogen, okay, we have hydrogen, nitrogen, hydrogen, then you can make use of the hydrogen. They can use the fuel cell systems. Okay, so you have a different combinations of the resource, depends on the availability of the resource, because we will discuss later on. One of the criteria of designing this microgrid, it has to be economically feasible. What does mean economically feasible? It means the cost of electricity that we generate from this microgrid, it should be competitive to the grid, if not better. Otherwise, what's the point? Especially if you have a grid connected. If you have a grid connected and then you tell me that the electricity I generate from microgrid is 3 times the grid, I better use the grid then. Yeah, the intention is to use clean resources, but there are many people, the first question they will ask is, what is the cost of electricity? What is the cost of energy that you generate? So that's why when we do the analysis, we do what you call a techno-economic analysis. Techno-economic means technical analysis. Technical means dealing with the technical components. What are the type of distributed energy resources I can have? And the economics. The economic is mainly 2 things. One is, what is the cost of electricity, which is the cost of kilowatt hour that we generate, based on the cost of the system that we design. And also we look into what we call renewable energy factor. Renewable energy factor means, for example, I generate 100 kilowatt hour of electricity. Okay, 100 kilowatt hour of electricity. How much of that electricity is generated from renewables? Maybe 70%. So maybe 70% is generated from renewables, 30% is generated maybe from a diesel generator or from the grid. So my renewable energy factor is 0.7. Okay, so because this is very important, because when we want to compare, the things we need to compare these 2 things, the cost of electricity, and I'm sure maybe some of you maybe have used the Homer software. This Homer software actually will help you to do this techno-economic analysis, and also do the sensitivity analysis. Sensitivity analysis where, for example, what will happen if I increase my solar? What will happen if I increase my battery storage? What will be the cost? What is the renewable energy factor? So I will have this kind of what I call this kind of analysis. We call it sensitivity analysis, because this sensitivity analysis will give us the idea actually what will be the best design options that we should have. Okay. Any questions so far? Anyone have any questions so far?
Sir, I have one question.
Yeah, please.
I just need to understand, as you mentioned, like the whole purpose of the microgrid is to go for the locally available resources. And you mentioned the micro hydro plant. Can you give me some idea of what will be the range of that micro hydro plant in terms of megawatt rating?
Okay. So depends on the, because when we design these micro hydros, it depends on the size, the amount of water flow. Because when we design the micro hydro, there are two factors. There is the Q, which is the volume of the water that flows, and then the speed of the water. So this, because sometimes you may have like a very steep river. So the speed will be very good. Sometimes you have the volume, the Q. So because we always, the micro hydro depends on two factors, which we call it the head, which is the height, and also the Q, the amount of Q. So it depends on the resources, but it can range from a few kilowatts to megawatts. Okay, it depends on you need to assess, because in renewable energy systems, one of the most important components is what you call site assessment, or we call them resource assessments. For example, if I want to install a wind turbine, so what I have to do? I need to do what I call site assessment or site selections. Assess what is the wind speed, what is the direction of the wind speed, what is the wind speed with the height, because as we know, as we go higher, the speed increases. This is very important. For example, I want to install solar power plant, solar photovoltaics. So what is the solar access? How many kilowatt hour per meter square? What is the directions? What is the best tilted angle? So this I would call site assessment and technical assessments, which gives you an idea what would be the optimum design, because we cannot over design, we cannot also under design things, so it should be optimum. Is that answers your question?
Yeah, mostly it answers us. Thank you for the answer. My whole intention asking this one, like in context, today people talk about SMRs, a small modular reactor, in terms of nuclear. So
Yes.
I mean, there is no defined rule for that, but typically around up to 300 megawatt, we say SMRs for nuclear. In that context, I was just trying to understand that what will be the typical range of
Yeah.
micro hydro.
Yeah,
I got yes.
Yeah, depends on the resources, depends on the amount, because micro hydro depends on the amount of water that we have. Yeah. So that's how we look at it.
And sir, one more question.
Yes, please.
You mentioned the advantage of going for the microgrid, which I understand there are a lot of advantages as compared with the typical grid. My question is related to especially on the stability and reliability part of the system. Okay, so if my intention is specifically on the dynamic behavior of the grid, considering the stability and reliability, in that context, which grid as per you will be more stable, microgrid or conventional grid?
Yeah, we all know that the conventional grid is quite stable, because you have this microgrid, as I say, it took almost 100 years to build. Okay, and the conventional grid is dependent on fossil fuel. So, for example, if I want to turn on a generator, a gas turbine, I just send a signal and then it will come up very fast. But for example, if I have a cloud that passing through the solar, and there is no wind, the intermittence nature of renewables, the intermittence, they are very intermittent and they are very weather dependent. So actually, that's actually one of the main constraints and the main challenges actually. But in terms of microgrid, one of the things is that which we discuss later, which can operate isolate. It can be isolated from the main grid. For example, you can operate in two modes, either in grid connection mode or in isolated mode. When you are operating in isolated mode, means if there is a fault, so it will impact only this microgrid. It will not affect the other parts, Or if there is a fault on the grid, then that will not affect this microgrid. So, and also maybe later on we will have maybe 2 or 3 microgrids interconnecting to each other. And these microgrids will help to support each other, and we call this phenomena self-healing capability. Interconnected microgrid with self-healing means they can self-heal in case one component in one microgrid fail, so they can self-heal things. So this we will be discussing maybe later in the control of the microgrids. Okay.
Thank you, sir.
Okay.
Thank you very much for answering.
Okay. So any other questions? Because in my lectures, I expect a lot of questions, either questions or comments or opinion, because we should be interactive. Doesn't mean it's online. I cannot see you. Means there's no questions. I prefer to have two-way communications rather than just talking to the screen, because I'm just looking to the PowerPoint and talking to myself. So it's good. And always keep asking questions. There is, like American says, there is no dumb question. There is no stupid questions. It's always questions, trigger something, and then maybe other people will benefit something else, Please, any other questions so far? Is this clear now? We see the traditional grid, and then we see the current grid is transforming, and then we're talking about the microgrid. Okay? Okay, I assume everything all right. Okay, so let's move. So the definition, let's define now. Okay, the microgrid. So it is a small scale power network supply networks. Okay, and is designed for small community. Means, what does it mean here? We have small remote communities, where maybe there is no grid. Okay, or maybe there is a grid, but it's not enough to supply, because for remote areas, when you do the grid extensions, you will have always a problem of voltage and frequency, okay, at the end of the grid. So you will have a lot of fluctuations of voltage and frequency. So what does the microgrid? Maybe it's a good solutions. Maybe it's an isolated. They don't have any grid. So it's enable local power generations for local loads. Mainly, most of these microgrids is meant to supply local loads, means existing loads within that community. Okay, and it consists of different what we call generation sources. Okay, which are flexible and also efficient. Most of them. For example, when we see a solar, means we say, but it's very flexible and also very efficient. Okay, wind, storage, so on. Okay, and it can be connected to also can be locally generating, and also can be grid connected in case to prevent outages. Okay, and you can even sell the power to the grid. Okay, means sell the power to the utility and buy from the utility as you need. So it's a two-way power flow. Okay, and the size of this microgrid, as I say, may range from housing estate to municipal to from few kilowatt to megawatt level. Okay, so this is the range. Because we have micro, we have pico. Micro and pico grids. This is a smaller level. So, for example, within your house, you can create a small microgrid. Small microgrid, which is, for example, your house within. You have solar. You have maybe, I don't know, generator, you have things, so maybe a small wind turbine. So that's one house, we're talking about few kilowatts, level, but it can go also megawatt levels, when we have a large community. Okay, so that will be okay. Okay, microgrid also uses the distributed resources to achieve independent for large power grid, from the large power grid. So we use a lot of independent sources, like I said, the main ones, which is usually the wind, solar, and the hydro, especially if it is available, run-off rivers. When we say run-off rivers, means actually you don't need to build what we call dam storage. So it is run-off rivers. And let me what we call here this point here. So this point here, for example, when you have excess power, you can sell to the grid. Yeah, that's actually a very good business model. Okay, so this actually can help you to reduce the payback, because most of these microgrids, they have certain payback time, you know, and this payback time is depends on the amount of electricity they generate, and you know, to offset the use from the grid and how much they sell, so they can get income from this. However, recently most of the countries have reduced what you call the FIT. You know, the FIT is the feed-in tariff. Feed-in tariff. The feed-in tariff used to be very high, especially if you generate from renewables. When we see very high means if your power is generated from renewables, I'll give you an example in Australia, like around 15 years ago. Okay, so the feed-in, the price of electricity, it's like almost 2 times. So if you buy from the grid, maybe it costs you 25 cents. Okay, if you sell to the grid, you can almost sell 50 cents per kilowatt hour. Okay, this is 15. I'm talking 15, almost 15, 20 years ago. Why? Because they want to encourage people to install solar and so on. Okay, so because when you have a feed-in tariff very expensive, so you can what you call your payback time will be reduced by half. Okay, what happened now after 15 years? Now, you know what is the cost of electricity now? When we buy from the utility, is 25 cents per kilowatt hour, but when we sell electricity from solar, is 5 cents. Because there is a lot of solar, as I say just now. We reach almost 100% in sometimes when it is very sunny and it's very clear. The amount of solar that injected to the grid, it reached almost 100%, 99%, even 100% in some states. 100% of electricity that is used is generated from rooftop solar only. Rooftop. I'm talking about the rooftop. I'm not talking about the large power plants. So that's why the companies now, the utility companies, they reduce the price of electricity that generated from solar, because now people are very because last time they want to promote it and they want to encourage it, but now it's becoming a mature industry. So what is the solution? The solution doesn't mean that we have to stop installing more rooftops. The solution is to have storage, to have a local microgrid community. So we have a local microgrid, interconnected the local community, and then we have a local storage where we can store the power, and then we can use it at night. We don't have to sell to the grid. So this is the trend now in Australia. We have what they call a community storage system. So what we have, it's a because what you have your electric vehicles, for example. We have a lot of people now have electric vehicles. So you can actually during the day you can charge the electric vehicles. At night you can plug in your electric vehicles and then use this energy to supply your home instead of buying from the grid. So this is a trend. So that's why I say there's a lot of flexibility, the microgrid systems. Okay. All right. Any questions so far here?
Is it necessary? I have a question regarding this. As you mentioned, excess power we can sell to the grid. Is it necessary all the microgrids should be connected with the grid, or just an option?
No, it's not necessary.
It's not.
But if you have the grid available, yes, it's a good option to connect, because that will reduce your, because if you have a microgrid and then you have a grid. So you have an option that instead of storing the power, you can inject to the grid, and then you can use later. So you can reduce the cost. That's why I say this need to be like there's a techno-economic analysis to be done to see what is the best. Am I going to do on grid connected? Because in the grid connected, you will put the price of electricity that you sell to the grid, and then at night you will use. So it is an option, but sometimes you may not have the grid there in that locations.
Okay.
Yeah.
Okay. Clear.
Okay. Any other questions?
Excuse me, sir.
Yes,
Morning.
please.
So the microgrid is it a DC grid or AC grid or both, sir?
It can be either an AC microgrid, it can be a DC microgrid, it can be a hybrid.
Okay, sir. Okay, thank you.
It can be one of the options, depends on the load, depends on the resources available, and so on. So it can be combined. We will see that in the coming slides.
Thank you.
Okay, good. Any other questions? Okay.
Good morning, sir.
Yeah, sorry.
Sir, I want to know about the Microgrid and the Microgrid difference between.
Sorry?
these two, sir.
I didn't hear
I
you.
want to know the different Microgrid and the Microgrid difference.
Difference between?
Microgrid and the Microgrid.
It's the size.
What's
It's
the
the
range?
size, you know. Yeah.
Voltage range of these two.
No, Microgrid means talking about something less than 5 kilowatt. You're talking about less than 10 kilowatt. Microgrid, you're talking about few kilowatts and above. And the operating voltage, it depends. We can operate at 48 volts. We can operate at 120 volts, you know. But, you know, if DC, most of them, we operate at either at 48 volt or 96 volts. Okay. So at DC. If it is an AC, then we follow the grid, the standards grid, which is the 220, I don't know, depends different countries, 220 or 110 volts, you know, 50 hertz or 60 hertz. Okay.
Okay, sir. Where we have used that Microgrid, sir?
Sorry?
Where we can use the Microgrid?
Yeah, as I said, at your house. If I have, for example, a solar on my rooftop, and they have battery storage, and they have an electric vehicle. Okay, I can become a Pico. Yeah.
Whether the Microgrid is might be a AC or DC, sir, or both.
Yeah, it can be most of the time. Most of the time, it should be a DC because most of the sources will be DC. But however, if you have an inverter, then in the PV, then you can operate, and then you can have. So it can be. I see. I give an example. One of the areas which we have actually working now, you know, even within the house, for example, the kitchen, kitchen can be a small Pico grid, you know. We call it a DC load. Sorry, not a Pico grid. DC load means because in the kitchen, what do you have? You have the cooking, right? Induction cooking. We can use DC, right?
Yes.
Fridge. Fridge is DC. Because now we have DC fridge, you know, when you go and buy a fridge, they tell you this is an inverter-based fridge. So it's a DC. When we washing machine, for example, we have a DC, we have an inverter-based washing machine. When you know, everything's it can be a DC actually, light, it's an LED light, it's a DC. A TV, it's a DC, it's an LED TV. So most of the loads now actually can be in air conditioning. In air conditioning, when you go and buy an air conditioning, they will tell you this is an inverter based. What does mean an inverter based? It's actually you can operate it on a DC. Yeah. So
sir, for house energy management, whether we can prefer a Microgrid or Microgrid, sir, home energy management.
Yeah, as I say, it's within a house I can see it's a Pico, you know. You know, it's a smaller size compared to, or you can, if you want to call it a microgrid, there's no harm to calling it. But microgrid is meant, for example, kilowatt, like I said just now, from kilowatt to megawatt levels, you know. So that's the things. But it doesn't matter actually what is called. What is matter is how this energy management between these sources and the load works. Yeah? You may have a harmonized AC and DC like we will see later. Okay.
Okay.
All right. Thank you. Okay. Let's move.
Thank you.
Okay. Thank you very much. Okay. So why do we need these microgrids? The question is, why do we need it? Okay. So microgrid could be an answer to the energy crisis. Yeah. Because why? Because it is one of the big issues that we mentioned in the traditional grid. Most of the generation are placed very far away from the loads. Okay, very far away. When you see very far, we're talking about thousands of kilometers. I'll give you an example. You know, I'm not sure you know or not, but this the Three Gorges Dam in China. The Three Gorges Dam is the largest hydropower in the world. It's 18 gigawatts. This hydropower plant is located where? Located in a state called Yichang state, you know, Yichang, in the middle of China. You know, and in that place, they have a lot of floods, so they build this Three Gorges Dam. Three Gorges Dam is 18 gigawatts. So in that area, they don't need the power. It's almost a remote area. The power is needed in Shanghai, Shenzhen, Beijing, and Hong Kong, and so on. So they need, what they have done, they have to transmit the power. It's using a DC transmission from this Yichang city, Three Gorges Dam, to Shenzhen and Shanghai and Beijing, thousands of kilometers. So, so even if it is, you know, made of hydro, but you have to transmit. When we see the transmission, means there are a lot of losses and the costs. But the microgrid is meant to locally use the local resources to be used, consumed locally. So that's actually can be, and then we can eliminate totally the transmission losses from zero. As I said before, the transmission losses account for almost 18%. And when we see 18%, you know, don't take it lightly. You know, 18%, it's $1 and cents. When you see 18% of 1 kilowatt, you know what does it mean? 18% of 1 kilowatt is, we're talking about almost 200 watts. When I say 20% of 1 megawatt, it's 200 kilowatts. When I say 20% of 1 gigawatt, so you can account the amount of saving and the losses that is in the transmission lines, and then the cost and the maintenance. You know, you have a tree grown, you have to cut it, you need to maintain. There is always animals passing. There is always short circuit. There is wind, subject to disasters. You know, these transmission lines will cut off and so on. So there's a lot of expenses actually. So that's why the microgrids is one of the solutions actually to solve this. Even there is a problems, will be localized. Okay. These microgrids, result in substantial saving in terms of, you know, cutting the emissions, because we, as I say, we're using a lot of local resources, and that's actually helps a lot, and provide a high quality and reliable energy supply for critical loads. Okay, and this is actually very, very important when you see critical loads. I'm not sure you know what that means, critical loads, because we have loads, we have also critical loads. Loads, well, for example, you have lights, or you have air conditioning, or you have a washing machine. For example, you are washing, and then suddenly the power cut off. What will happen? Washing machine stops. Are you going to die? No. By the washing machine stops. If the light goes off, are you going to die? No. But there are some critical loads. Anyone knows some critical loads? Can you give me an example of critical loads?
Medical loads, hospital loads.
Yeah. Even the hospital may be not critical. Maybe one part of the hospital, for example, the operating room in the hospital. Yeah. So that is very critical. For example, the surgeon is doing the operation, suddenly the light turns off. Yeah, we are losing people life. Any other examples of critical loads?
Perhaps the control, communication of certain critical equipments.
Others? I give you
data centers.
Sorry?
Data centers.
Data centers, yeah. For example, yeah, you have data centers. You have, if for example, suddenly banks or this Google or for example this AI, DeepSeek or ChatGPT, you know, or this Alibaba or this online, you know, stop, suddenly everything collapses. Other critical loads. Now, one of the very important also critical loads is airports. So imagine that a plane is landing, you know, suddenly the runway turned off. Where are you going to land? Maybe land in the mountain, you know. So airports, for example, these are critical loads. Means it has to be, you know, even there is standards. You know, the light cannot be cut off more than one. How many seconds? You know, we're talking about seconds. Cannot be. It must be. So this kind of critical loads, you know, one of the solutions to address these critical loads is the use of these microgrids. Means you dependent on the locally produced and locally energy, which is you have control on, and that's what is called reliability. And sometimes we may have a redundancy also. Sometimes, okay. For example, we have storage, we have a diesel generator. Why we have these two? Why we have diesel and diesel generator and storage for some of the loads? Why? Any idea? Oh, because I give you an example. One of the factories which I visited recently, which is the wafers. You know, they're making the electronics, making devices like diodes and IGBTs. When the wafer comes in, this wafer, you know, cannot stop in any way. It has to end up to the packaging. You know, the device come out. If it stops halfway, you have to throw everything out. Imagine that the power cut off. What happened? So the wafer gone. You know, that's a wafer, very expensive. So most of these factories, they will have redundant sources. What such as, for example, they have a diesel generator and then they have the battery, UPS system. Why they have both? Any idea? And even in the battery, they will have super capacitors, battery, and diesel generator. Any idea why they have this kind of redundancy?
Battery too, because battery is the one which we can rely on when there is a power off. The battery is the one which is the most reliable source. So it will take immediately the power supply for wherever we require the critical loads, but it has, you know, cost and because we cannot have battery very big size, it will have cost and other complications.
Yeah.
So we need to keep it charged. So for that, again, we need some source of power which will be DC, but it has you know, some time to start up. So first switch on the critical load on battery, then turn on the DC, keep the battery charged, and that is how we can maintain the reliability.
Very good. Yeah, that's good. Very good. Yeah, actually, the combination is meant because batteries and supercapacitors provide a very fast response. Diesel generator will take some time, few minutes, you know, to turn on, and then takes time. So for the first few minutes, maybe we have the batteries, supercapacitors much faster. Okay, but they have a very low energy density. Okay. They have high power density. Batteries have a high energy density, but low power density. So supercapacitors, batteries, and then diesel generators. So we have this combination. Most of the industries, they have batteries and also diesel generators. Yeah. So that's the answer. So that's the combinations. Most of the time we have this kind is to increase the reliability and the what you call the secure power, you know, to the load, especially for critical loads. So these are some of the listed benefits. Some of the benefits of the microgrids. Okay, with respect to the traditional grid. Okay, again here, very important here. I think this point here. I don't know if you see it or not. It has to be well designed. What do we mean here, well designed? Any idea? Because sometimes you may design a microgrid and then you will have adverse result actually.
Well designed means it should be not too big. I mean, we should to take care of, you know, it cannot be over designed. I mean to say, because it has a lot of is capital intensive solution, so we have to take that in the mind.
I think, sir, we can add point to that for well designed, we mean that we need to have an optimal size of a microgrid, so that both in terms of economical point of view as well as from electrical point of view, so that there is power balance at every instant of time.
Yeah, I think that's the answer. So it's well designed. It has to be well, you know, calculated. You know, it's not like you know, take a pencil and paper and then do this. I want to have this solar. I want to have this. I want to have microgrid. No, it has, as I said before, there are some softwares which do for you the sensitivity analysis. You know, what we have, if we increase the battery by this size, what will happen? If we increase the diesel generator size, what will happen? What we have increased the number of panels, what will happen if we have clouds, what will happen this. So this analysis is very, very important. And also, you know, it has to be, what is the objective of this microgrid? Because sometimes we design this microgrid not to provide the power, but it's just like a demonstration. You know, for example, I want to make my renewable energy factor 100%. Do you understand what is a renewable energy factor or not? Anyone knows?
Percentage of total renewable in the total generation capacity.
Yes, good. Yeah. So the renewable energy factors is, so for example, if my objective is to have 100% renewable energy factor, so I have to maybe increase the amount of solar, the amount maybe of wind, the amount, because the target is to be 100% renewables. But if my objective, for example, is to have a cost-effective what you call electricity supply, then I need to balance. You know, I may have this amount, this amount. So this is because in any design there must be an objective of the design. Okay, what is the objective? Okay, is it the objective to have a reliable electricity regardless the cost? Okay, because there are some applications where the cost is not a factor. Okay, can you give me an example?
Perhaps, yeah, perhaps one example I can say is like offshore platforms, because it is remote location, so they are more than, I can say, money. The reliability is more important.
Yeah.
Another example can be of ventilator loads in the hospitals, because there we need to save life rather than we should focus on the economics of energy.
Okay, but all of this you can see, for example, even the offshore platforms, we can still bring diesel. If we have a diesel generator, hospitals, we may have batteries. There is one application where the cost is almost negligible. Cost is not a factor. Is the space applications. You know, satellites. Satellites cost is never a factor. No one tell you, because they count millions and millions. And India is one of the leading countries in space. You know, because space satellites or space ships, you know, they are a microgrid. It's a microgrid system. They have the largest part of the spaceship is all the solar panels. And they will have the most expensive solar panels, these multi-junction solar panels, to increase the efficiency up to almost 40%. And then they have the high density battery systems. So because the cost is not a factor here, it's the reliability, because they cannot lose power. So they will never consider cost at all. That's why most of this space will be very, very expensive, because the most important is the reliability of these systems. Okay, and plus, like we mentioned just now, offshore also, maybe the cost is considered, but not maybe that's important. Maybe some hospitals, critical loads, and so on and so forth. So that's why I say that you need to know, you know, because this is in all renewable energy systems. They are location specific, you know, and the design have to be a location specific. Okay, so means location specific means you need to know the environment that you are going to install these microgrids. For example, if it is a space, then you have a different dimensions, different objectives. If you're having an offshore platform, that is different objectives. If you're having a hospital, it's different. If I have my microgrid is just to provide, for example, lighting to the homes within a community. So this is maybe the most important.Maybe will be the cost. Okay. All right. So that's the point of the well design. So it is more reliable. Okay, with diverse input of power. It's more efficient. very environmentally friendly because it does not because it uses local resources like I said. Very flexible. What does mean flexible? Means you can add another source, we can remove, we can change, we can extend, we can increase. Okay, it's less vulnerable to disasters because it's not connected. It's not big. It's not huge. It's locally. It's one. This is very important. What does mean modular? Anyone?
Modular means we can increase the size just by adding a similar module.
Yeah, so we can add, for example, we have a 10 kilowatt, 5 kilowatt photovoltaics. Suddenly our village gets bigger. We can make it 10, we can get 20, so on. And also easy to control because the local control just control the energy management within these sources. It's very, and also it's immune from any grid issues because it can, when we design this microgrid, it can operate in both mode, as I said before. You know, it should be able to operate on isolated and also grid connected, most of them. Okay, especially if you have the grid. Okay. Okay. One of the main issues is the cost. That's the biggest. Always the capital cost is quite high because it involves all this. But what we do what you call when we design this, we calculate what you call the payback time, and then we see if the payback time is reasonable. How we see the payback time is reasonable? Anyone knows? Any idea? What does mean reasonable? When I mean see the payback time should be reasonable and should be realistic.
I'm not very sure, but I mean, perhaps as per the industry practice, if we could be able to get our investment back within, say, 3 to 4 years, I can say it is a reasonable period. Beyond that, it will give profits.
Good. Yeah, 2 to 3 years. Any other questions or any other suggestions? What is the reasonable, what you call, payback? I hope everyone knows what is the payback, right? The payback is, for example, I invest certain money, okay, and then how much time take me to recover the money that I have invested, okay? Okay, most of the time, the reasonable, like our colleague mentioned just now, it's 3 years, 5 years, because something more than 5 years, it's becoming too long. And becoming many other factors may affect this. And hey, by the way, I don't know the time. Anyone here, Dr. Siva is attending, or any other one who can? Because even when we start discussing, I forgot myself. Because we lecturers make money by talking, so we do a lot of talking. So when we talk, we never stop. So please let me know.
You can go ahead.
So how much time we have for the first lecture?
Yeah, up to I think 20 minutes is there. You can go for 20 minutes.
Okay, so around,
you have finished your content then?
No. Content we never finish.
Yeah.
Content we never finish, but I don't want people to get bored, for too long, So that's I think the first one is 1.5 hours, 1 hour 15 minutes, right?
Yeah. If it is anything else is there, we can take a break at 45 minutes, and then you can start again next time. Okay.
So let's finish these slides, and then we So microgrids, I do a lot of talk. I hope the participants are able to catch up because not everything in the slides I mentioned. I mentioned lots of things within the explanations, and that's the way. The slide is just a guide, but the main important part is the one what I explained is based on my experience designing these microgrids and so on. Okay, microgrids also can be integrated into existing systems, so these are good things. So it's not something new or something that we have to build from zero, but you can integrate to the existing without having to interrupt the loads. Also, microgrids allow for combined heat and power, okay, generations. So that's which is very, very important. Means you can do both. Okay, so these are some of the benefits. So there are also some issues. Okay, there are some issues with the microgrids. Okay, it is a load following, so it follows the load that you have compared to the normal grids. You know, so power versus energy profile for the storage, because as I said before, you have energy, you have a high density, you have a high energy, and then you have low power density, high energy density. You know, stability. You know, because for example, there is a drop in wind speed, there is a drop in solar irradiance, so that affects your voltage, and that affect the voltage, affect the frequency, and then the stability of the local grid. The cost, I think we have mentioned about it, the investment cost, which is quite high, and the big capital cost is quite high, but the maintenance cost is very low. Maintenance cost is very low compared to this. The architecture and design, I think that's very important. I think I mentioned about it, which is the well-designed. I think we have talked about it just now, the well-designed, and what are the components you have to do. And optimizations, everything that we do, we need to optimize. Okay, for example, if I change the tilted angle of my PV panel by 15 degrees, how much power I will get? So I need to optimize the tilted angle of the PV panels. I should optimize the orientation of the wind turbine. I should optimize the location of the micro hydro. I should optimize the size of the battery bank, you know, and the location of the battery bank, and so on and so forth. The location of the inverter. So this is all optimizations. Okay, and most of these microgrids will have autonomous control. Okay, so it's maybe in terms of security, maybe they can be hacked or whatever. So, but that's another issue. But most of the current micro hydros will have some protections, you know. Fault detection and mitigations. Okay, so this control system should be able to detect the fault and then how to mitigate it. And the last one, which is the grid connections. Whenever you have grid connections, you have a lot of issues. So because you need to match the frequency and the voltage of the grid, you need to, you know, there is sometimes, you know, the grid is highly variable. So there are some issues. So these are some issues that we usually face during the microgrids. Okay, another question is who can use the microgrids? I think we explained it before. I think one of them, which is sometimes especially critical loads, universities and research facilities. You know, we have in our lab here, we have actually a microgrid, one building, okay, two buildings which are two microgrids and connected to each other. So the whole building is a microgrid by itself. Smart cities and communities, you know, so most of them actually they prefer to have microgrids to have more reliable and more independent. Government buildings, offices, also it's a trend to have this kind of microgrids. Utility microgrids. Sometimes you may have a utility microgrid. Okay, that is to split the military facilities. Also, this is very common. Most of the military bases usually are remote, and sometimes maybe they've been displaced. Moved. They move. Military usually move from one place to another place. So most of the time they move to places where they don't have power. So they have to have their own microgrids. So they have to build. Okay. Right. Like our friend just now here, the offshore stations, gas stations or stores. So these are some of the microgrids where they can be used. Okay. All right. So it's maybe another 10 minutes and then we make a stop. So 1.5 hour first one. Okay. So what are the main components? Okay. So the main components of the microgrid. Okay. If you look into first one, the distributed generator, usually mostly renewable energy sources, such as wind, solar, micro hydro, whatever, and also diesel generators. Okay, most of them is usually we use like this. Like for example, we have solar, we have wind, we have diesel generators, we have, for example, fuel cell. It can be a component that be used. Storage also can vary. And most of us knows only the batteries, which is the conventional one, but we can have the ultra capacitors. Like I see, the ultra capacitors has a very high power density, but low energy density. So they are faster than the batteries in terms of response. And one of the applications of this ultra capacitors, for example, for electric vehicles, and especially the Formula One racing cars, electric cars, they use a lot of ultra capacitors. The ultra capacitor, because they are very fast. They can give the speed, the amount of energy very fast. They can discharge very fast. They can discharge very fast to give the power so you can reach the speed that you need. The batteries will not give that amount of, they don't have that speed, of discharging. But they charge very fast and they discharge very fast. However, the batteries charge very slow and discharge very slow. So a combination of these two will give you, good balance between the power density and energy density. Also, we have flywheels. Also, flywheels is another way, which is actually a mechanical. It's like spinning, So that's also can be a fuel cell. Okay. So sometimes we may use, if we have excess of power, sometimes we may have excess power in some microgrids. So what do we do? We have an electrolyzer, and that electrolyzer generates hydrogen. Because like I said before, sometimes selling the power to the grid is too cheap. So what we do, for example, if you have an electrolyzer, and then you can generate hydrogen, and then later on your hydrogen, you put it into the fuel cell, then you generate electricity. So you're becoming automatically like a storage, and then also you can use it whenever you need. So that's the fuel cell. Yeah, there are a few companies and few big companies start using this kind of technology, especially when you have a green. We're talking about the green hydrogen, because, like I said just now, one of the problems that we are facing now in Australia is during summer, we have a lot of excess of renewables, especially from solar. We exceed 100%. I'm talking about 100% in certain times, which means the whole state is powered by rooftop solar. So what does it mean? It means all the coal power plant, all the gas power plants have to shut off. And that's not good, because the solar can dramatically drop very fast. So, and that's not good for the grid. So one of the ways is now, which is now actually the Australian government is pushing very hard, is how we can make use of this excess electricity power that generated from solar to generate green hydrogen. Okay, so this green hydrogen, and then store it, and then use it whenever you need. Okay, so because when you have excess power, so you don't have to pay any additional thing. So if you have electrolyzer, I'm talking about not at home, but we're talking about stations, large stations, where we have, and then also storage, which is one of the way of storing. And then also they start talking about this pumped hydro, where they can pump, when you have extra power, you can pump back the water to the upper reservoir and then use it later on. So these are some storage techniques. And then we have the loads. Okay, so these loads can be AC loads, can be DC loads, can be a plug-in car, or electric car, an EV car, or or the main grids. Okay, and what you can see also, in order for this microgrid to work, there is one green box here common among all. What is it?
power electronic interfaces.
Yes. For all of this to work, you need the power electronics interface. Why do we need the power electronics? Any idea?
For AC to
For
DC
power
compatibility?
For power conversion.
Yeah.
Yeah, power conversion. Because we have different sources. Some sources are AC, some of sources are DC.
DC.
Some of them loads are AC, some of DC. Some of them they operate at higher frequency, different frequencies. So you need the power electronics. So the power electronics is a very important component here. And some of these power electronics, they are bidirectional. Can you give me an example, a location where these power electronics have to be a bidirectional device?
Battery charging.
Wherever you have energy storage.
Yes. Storage, yes,
You
good.
need to have a bidirectional.
How about this?
From grid to energy storage, from PV to energy storage.
Yeah, grid also have to be bidirectional, so it has to be very bidirectional directions.
PV to grid.
PV, no. We don't
PV
store.
to grid.
Sorry?
From PV to grid also we can do. No, sorry, I'm sorry.
No, PV we cannot.
No.
PV cannot. PV we don't do PV. We do only storage, grid to load, or to the thing we have storage. Means the power here can go from energy storage to the grid, and then from the grid to the storage. So it's a different control. So, and this can be, when we say power electronics, what do we mean? What types of power electronics? We're talking about DC-DC converters, right? We're talking about inverters. We're talking about rectifiers. So these are the power electronics. So, for example, in a grid to the microgrid, you need the bidirectional, what you call inverter, right? Bidirectional inverter, which can convert from AC to DC and DC to AC. For example, from battery also, you need a DC-DC converter here for battery, because DC, for example, and then maybe you connect to this an AC microgrid, then you need an inverter. So depends on where the locations that you need this. So these are the main components, as I said, but you can pick and choose which one is suitable for your applications. Okay, I think maybe we it's already 1 hour 30 minutes, so maybe you can have a break, Dr. Siva.
Yeah, you can go ahead.
How long the break?
No, break is fine. You have finished the 1.5 hour lecture. I think as per the schedule, we are done at 10:30 to 12. Maybe again you can deliver the lecture on tomorrow.
Oh, for today, that finished today. Yeah. I thought today we have 2 lectures, right?
No. It is 10:30 to 12 now. In Indian time.
Oh, today is only 1 lecture like this, only.
Yeah.
Because I still have a lot of content,
Maybe on tomorrow you can cover it and make it up.
I don't know.Maybe we can open a few questions for the participants. We have another maybe 5 minutes. If you have any questions, as I say, I explained a lot, during the discussions,
Correct.
So maybe most of the information is not in the slide, but we will go into detail all this. So anyone have any comment or any questions or any inquiries, please feel free.
Sir, I just need to understand one thing.
Yes.
In terms of today, like in context of hydrogen, there is a lot of discussions happening for green hydrogen, and we understand primarily green hydrogen means the sources should be completely the renewable power. Okay.
Yes.
So I just need to understand what exactly the green grid. Is it mean that this grid has no fossil power, fossil fuel based generation, 100% renewable, or how? I am not very clear what exactly meant by the green grid.
Yeah. If you're talking about the green grid, if you're 100% green, there's no. You can have a green microgrid, but you cannot have a green grid. It's impossible because it's 100% power. But 100% renewables You know, it's almost impossible at the moment. Maybe in the future we will have it. There are some countries, for example, which achieve, for example, Denmark. Denmark now, at the moment, 60% of their electricity consumption is generated from wind. Okay, and they have the target to achieve 100% by 2035. So what does it mean? It means the electricity that is being generated during the time is 100% from wind. Like I see just now in Victoria, for example, we have reached to 100% power, not all the day, during a certain time during the day for 1 hour, something like that. I have the graph. 1 hour, 100% of our load is supplied by the grid. From during that time is a green grid. Okay, but as you know, the grid requires the inertia. Okay, and the inertia, these renewables does not provide the inertia that's needed for the grid, you know, to maintain the frequency and the voltage. Okay, so at the moment is trying to introduce as much as green resources into the existing grid and try to maintain the stability. And that's why you can see the research in power electronics. Now we are moving from grid following to grid forming inverters. So these grid forming inverters actually need to help stabilize the frequency of the grid, not only just injecting the power. Last time it's only injecting the active power, and then now reactive power, and then now it has to help in stabilizing the grid. So that is the future. The future is to move to a green grid, which is mainly from green resources, or when we see green, sometimes also we may see a carbon neutral, you know, grid. That's what sometimes we see it's carbon neutral. What does mean carbon neutral? It doesn't mean it is 100% renewables, but it's neutral. Means actually you can offset. You can generate some carbons during the generation, but you can offset that carbon maybe through some other means. Okay.
Thank you. There are certain discussions. Maybe it's already 12 o'clock. I'll just take 2 minutes here. There are certain discussions that Prof, perhaps I'm not very sure it will work out or not, but to have, you know, one conventional grid where it can be a combination of fossil fuel plus renewables, and one having completely green, means only the sources or renewable will be connected to that, and that will be a green grid. So there could be two grids, one conventional, one grid. So connect all the renewable sources to one grid and make it as a green completely, and one as it is what we have. Can you give us some feedback on that? Is there any certain development happening in this area? I mean, very high level information I just have.
Yeah, as I told you, yes, there are a lot of push now into trying to make the grid as green as possible, or as carbon neutral. That's the term. I prefer to use carbon neutral grids rather than green grids. Yeah, green grids, yes, it is just a term, but as I say, it's still very, very far away. Okay, so what's actually happening now what's happening now, the big issue is how to manage this kind of penetrations that is from renewables. You know, how we can maximize the penetration, because now there is a certain limit actually of renewable penetration to the grid, you know, and that will lead, if we exceed it, the grid may lose the stability. So that's the discussions or the thing. So to build the new grids, new grids, yes, actually it's a greening the grids. Maybe greening it means by introducing more renewables, reducing because even in the current grid, the traditional grid, there are 3 levels of pollution or polluted. The coal is the most polluted one. So if you want to make a grid greener, remove the coal from the generation. The second one, which is the oil. The third one is the gas. Gas is the cleanest. So if you can actually reduce the coal and the oil, okay, and maybe keep some gas, and some nuclear, actually that means you are decarbonizing the grid, you know, because we have the 3Ds, you know, we call them the 3D, you know, the decarbonization, the grid, decentralize it, and digitize, digitize, decarbonized, and distributed. So this is the trend, you know. So the steps is like this: to remove the dirtiest component from the grid first, which is the coal. Like for example, Australia, they have put 2028 or 2030 will be the last coal power plant to operate. So what does it mean? You need to replace this by what? By gas. Gas is cleaner, okay, but it's not green. Okay, so introducing more winds, introducing more storage, introducing more what you call green hydrogen. You know, so that actually will help to green up the grid. But it will take some time.
Sir, 4D you said decarbonization, decentralization, digitization, and what was the other D? The
3D. Digitize, distribute, and decarbonize. Yeah.
Okay, 3D only. I heard 4D.
Yeah, 3D. Yes. 3D.
Okay. Thank you.
Any other questions?
Yes, I think no questions. I think we can continue in the next section in the afternoon at 2:30.
Tomorrow what time?
Tomorrow.
Today do we have another session?
No sessions. Today is no session.
Tomorrow what time?
Tomorrow at I just a minute.
Yeah, because I need to confirm.
Correct. Yeah.
And especially India, you have the half an hour.
Yeah.
That is confusing.
Tomorrow at 2 p.m. in the Australian time, 2 p.m. to 3:30.
Can I have a request? Can we make it 2:30? Is it possible?
Then it goes to you have 2 sessions in the tomorrow. Maybe it goes up to 6 p.m. in the evening. Is it fine?
That's fine with me. But 2:30, is it okay?
Yeah, then fine. I think everyone is there. I'll reschedule it to 2:30.
Yeah, please. All the participants. So can we start tomorrow at 2:30?
Yeah.
Australian time, which is
at
9, right?
9
Indian time.
Yeah, correct. No issue.
Is that okay, Dr. Siva? Or if it's not, I have to make arrangements. Is it okay?
No, it is fine. It is fine. No problem.
Okay.
We'll
just half an hour shift.
Half an hour shift. Nothing. Yeah. Thank you, Professor.
Okay. Thank you very much for everyone. And I hope tomorrow I will have a lot of questions and comments. Please.
Yeah.
Okay. Thank you.
Thank you, sir. Thank you very much.
Thank you. Bye-bye.
Thank you.
Attendance link.
I shared in the chat box.
I'll check.
Please.
Sir, please do share once again.
Yeah.
Please do share once again, sir.